Okay, so do you guys have any questions or specific problems you want me to go over first?
Not really.
Okay. So I have a couple problems up here on trusses and frames. Now, can either of you tell me what the difference between a truss and a frame is?
Is a frame, a truss uses like rods, while a frame uses
Yeah, that's pretty much true.
moments.
What?
Frame also doesn't resist about the moment. So.
The frame does resist moments, whereas a truss doesn't. So basically, a truss is just a type of a frame that uses sled rods. So in this case, this one is going to be the frame. This is a truss. So you'll see in the analysis done here what the difference is as far as how you're going to do the calculations. So first thing, let's just do a free body diagram of this. Just get out. Just make sure that this is still recording. Okay. Okay. So this is a frame. So the first thing we want to do is just do a free body diagram of the whole thing. So that's pretty much the frame that's drawn without joints. And now we want just a 20 kip force acting here. We have a roller here, so it's going to give us a force perpendicular to the ball. We'll call and mark it up here. And put letters here for the joints. So A, B, C, D, E. So we'll call this one EX. And we have a pin support up there, so that's going to give us two reactions. So we'll just call that AY and AX. So this is, you would do this regardless of if it's a truss or a frame. So just going to do some of the forces in the X. Will give us AX plus EX is equal to 0. Some of the forces in Y give us AY minus 20 is equal to 0. So that's the 20 kip force there. So that just tells us AY has to be 20 kips. And then we need a moment equation to get these other reactions. So let's see. So you want to take it about point A because there are two forces there. You could take it, since we know AY, you could take it about point E as well, but that will just be more work. So we'll just do it about point A. So first we want to look at how far away EX is and do a right-hand rule. So it's 4 feet downward. If we do a right-hand rule, your thumb will be pointing out of the board. So that'll give us a positive moment. So 4 times EX. And then do the same thing here for the 20. It's 5 feet over. And if you do a right-hand rule, your thumb is pointing into the board. So it's going to be minus 5 times 20 is equal to 0. So this will just tell us EX is equal to 25 kips. And obviously from our first equation here, we have AX plus EX is equal to 0. So AX is just the opposite of EX. So it's negative 25 kips. So there's all our reactions. Now the problem asked us to solve for all of the forces acting on this number here, ABC. And this is where it gets different from a truss. So let me just open a new page here. So if we draw a number ABC, So we have the two reactions here from the pin joint. This was 20 and negative 25. And then we had point C and point B both have pin joints there. But in a truss, these would just, the forces due to these would just be along the axis of the member. So you would have one force acting this way and one force acting this way. But because of how these members are connected, you have forces that are acting along, like within the member. There's pin joints within the member. If there's only forces acting at the two end joints, then you would just have axial forces. But here we're talking about forces that are not along the ends. So you have to solve that differently. So for example, for this member C over here, we don't know what direction these forces are going to act. So we just mark it as two reactions. We have CY and CX, whereas if it were a truss, you would only have a reaction going in the X direction. Now, member BE is sort of tricky here because it actually follows, let me just draw out BE by itself here. So if we look at just member BE here, okay, so it's connected to two joints here. And so if we're saying that we don't know the directions here, since it's about the endpoints, known as a two-force member, which means that if you do with some of the forces in the X and some of the moments, and it'll give you, eventually, it'll give you just two forces acting along the axis. So because it's about the endpoints, there aren't any forces that are acting here or anything. We know it's going to be along the axis. So when we're doing our analysis of that point, we can just say that it's a force BE acting in the direction that our line BE was acting. So this was this line right here. We can just draw this as a triangle to simplify this out a bit. So first we need to look at how high up this point is. So we can do that using similar triangles. So imagine this is point A, point B, point C, D, and E. So we know this is 4 feet up, this is 5 feet, this is 5 feet. So we're looking for this length of BD here. So if we do 4 over the length, 10 feet is equal to X over this partial length here of 5 feet. It's pretty obvious that it's just half of, since this is halfway over this way, it's going to be half of the height here. X is just equal to 2 feet. So knowing that, we can write in this is 2, this is 5, and this turns out to be square root of 29. So we can use that in our calculations. So we can start doing some of the forces on this entire number.
So the 20 kips at joint B doesn't affect anything?
The 20 kips at where?
Is the 20 kips acting on B?
We had a reaction at joint A that was 20 kips, but there wasn't anything at joint B yet. This is acting at joint B. This is just showing that point B is in line with point B, point D is in line with point B, and this is acting at point B.
Okay.
So it's actually acting on this bottom number here.
Okay.
So now let's just continue with some of the forces in the X. So we have our negative 25 there. We're going to have part of BE here. So since that was in the X direction, it was going 5 feet. So we do 5, or sorry, it's not going to be plus because of the direction here. It's going negative in the X direction and negative in the Y direction. So if we're looking for our force BE here, since the entire length was square root of 29, we just do minus 5 over square root of 29 times BE. So that'll give us our BEX. And then, let's see, then there was one more from CX here, so plus CX is equal to 0. We can't solve that yet because we don't know either BE or CX. Now if we do some of the forces in the Y, we can get a similar thing here. We have 20 plus CY, and then minus that BEY. So that was the 2 over square root of 29 times BE is equal to 0. And again, we don't know CY or BE. So we need to move to a moment's equation to get it. Now, where do we want to take our moment about? Well, it's probably best to take about point C since that's at the end and we don't know either of those forces. We can figure out what BE is because BEY and BEX are related, and then we just have to look at that. So I'm going to do this as a vector equation just to try to make it a little bit easier here. So we're looking at this point here. This was 10 feet in the negative X direction, and it was 4 feet up. So to write that as a vector, we just say negative 10 I hat plus 4 j hat, and we're going to cross that with both of the forces there. So it was negative 25 I hat plus 20 j hat. So that's the moments due to the forces there. But then we want to add moments due to BE. So let's see, so that one was half the distance, so it's negative 5 and out 2. So minus 5 I hat plus 2 j hat. And then we need to break down BE into its components. So we have the magnitude of BE and then times the direction vector. So it was, let's see, it was negative 2 I hat minus, sorry, no, negative 5 I hat minus 2 j hat. But that's not a direction vector because the magnitude isn't 1, so we have to divide by the magnitude of that, which was square root of 29. So that gives us our entire moment equation, and this is just equal to the 0 vector. So now let's start doing the calculations here. So we have the negative 10 I hat cross negative 25 I hat, that's 0 I hat cross I hat. So then we move on, negative 10 I hat cross 20 j hat, that'll give us a positive k hat value for I cross j, but it's negative because it's a negative times a positive. So that'll give us negative 200 in the k hat direction. And we have j cross I, which will give us a negative k hat, but since we're multiplying by a negative number, that'll give us a positive. So plus 100 k hat. And then we move, since it's again a j cross a j here, that's going to be 0, so we can move on to the next one. So I cross I is 0, I cross j will give us a positive k, and it's a negative times a negative, so it'll give us a positive as well. So plus And we have to multiply all of this out, so it's going to come out to 10 BE over square root of 29. So that's just from the 5 times BE over root 20 times 2. And if we do the same thing with this J here, we actually end up with the same value, since we have a J cross an I. That's going to give us a negative K, but since it's negative 5, we know it's going to be positive as well. So this turns out to be the exact same value. So now that we have that, oh, and these are both in the K hat direction. So now that we have that, we can just simplify here. So this is equal to the 0 vector. So taking it out of vector form, we have negative 100 plus 20 BE over square root of 29 is equal to 0. Move the 100 to the other side, multiply by root 29, divide by 20. So that's 5 over root 29. Sorry, not over root 20. 5 root 29. And that turns out to be, let's see, 26.926 kips. And so now that we have, that's the magnitude of BE. So this is equal to BE. Now that we have that, we can just plug those into both of our force equations to get Cx and Cy. So when we do that, we just get Cx is equal to 50 kips, and Cy is negative 10 kips. And so that's the end of the problem there. We solve for all the forces acting on number ABC. So there are just 3 main forces here. And this also shows how a truss is different from a one of these. So let's see. So this one's the truss. This one should be a lot easier, although it's obviously a much more complicated truss. So we're told, oh, I forgot to write in the force values here. Let me just get back to this problem. Okay. So you just write in all these values here. 1 kilonewton, 2 kilonewtons, 2, 1.75, 1.5, and 0.75. We're also told the distances between these points here. These are all 6 meters apart. Okay, so first thing we want to do is a free body diagram of the entire truss here. So the fixed pin here is going to give us 2 reaction forces. So it's going to be AY and AX. This roller pin here will just give us 1 reaction, so we'll call that HY. And then, of course, we have all of these other forces acting down on it. So now if we do our sum of the forces, obviously if we do some of the forces in the x, there's only one force acting in the x. That's ax. So we know that's just 0. If we do some of the forces in the y, that's where all of our forces are acting. So we have ay plus hy minus whatever all of these forces add together. So let's see. So it turns out all of these forces are equal to 9. So pointing down, we can just do minus 9. And so that's equal to 0. They need a moment equation to give us the final results here. So if we do some of the moments about point A, we have force Hy times the distance of 18 meters there. And it's going to be, to do a right-hand rule, it's going to be positive. The thumb's pointing out of the board. And then all of these other forces are going to give you a negative value because the thumb would be pointing into the board. They're all pointing down. So, and since this force here is acting at point A, we don't have to worry about that. So I'm going to do, let's see, minus 2 kilonewtons times 4 meters. And we have another 2 kilonewtons, and that's 8 meters away. Minus 1.75, that's 12 meters away. Minus 1.5, which is 15 meters away. And minus 0.75, which is 18 meters away. And all of this just boils down to giving us Hy is the sum of all these moments divided by the distance there. So Hy turns out to be 4.5 kilonewtons. And knowing that, we can plug that into our sum of the forces in the y to give us Ay is also 4.5 kilonewtons. Now, it's not really a symmetric problem. Obviously, there are more forces on this side, but because they're spread further apart, it just happens that based on the numbers they gave us, these two forces turned out to be equal. So let's see. Now we want to start doing our joint analysis. Okay, so we can start at joint A. We have one reaction force here, which was 4.5 kilonewtons. And we have our external force here of 1 kilonewton acting downward. And then we have two members that were attached here. So this would be, we'll just call this AC and AB. And they're drawn in tension. So we also want to look at what angle this is at. So let's try and figure that out first. So if we draw this member here, so we have a 6 meters over, actually let's do, it's 12 meters over and then 6 meters up. So like if you're looking over to this point and then up to that point, that'll give us this angle here. So let's just check what that is first. Okay, so this length here just turns out to be 6 root 5. So we'll just use that in our calculations. Okay, so now we have that, we can start just doing some of the forces. Let's see. So since there are 2 unknown forces here that are acting in the x direction, we don't want to start with that, so we'll start with some of the forces in the y. So the only reaction here is going to be AB, which was in the y. So let's see. It would be the magnitude of AB times, let's see, it was 6 divided by the square root of 5 times 6. So 6 just cancels out here. And then we're going to have plus 4.5 minus 1. So AB is just going to be negative 3.5 times root 5. So AB is negative 7.8262 kilonewtons. So there's our first solution there. Now we can do some of the forces in the x to get our remaining force AC here. So this time it's going to be 12 times AB over 6 root 5. So this just cancels, makes this a 2 over root 5, and then we have plus AC, 0. So AC is just AB times negative 2 over root 5. And this turns out to be 7. So now we can move on to our next joint. We'll just look at joint B. So joint B here is just this joint. We'll mark this down here. A, B, C, D, E, F, G, H. Okay. So now we're looking at joint B here. It's going to have a force to solve for. We have a 2 kilonewton force acting down on it. And we have PD acting in the same direction. And then we're going to have BC. And so now we need to look and try to figure out what angle BC is acting at. So let's see. So I think we need to do a similar triangles thing here. So let's just draw this. So imagine this is AFE, and then this is B, and this is the height B is from A. So we're looking for this height here. We know that this height was the entire distance here is 12. And then from the other part of this, we know that this distance here is 4. So we can just do a similar triangles here to get the height B is. So let's see. It's going to be 6 over 12 is equal to x over 4. So that's just 1/2. So we know x is 2. So if we're drawing that as a triangle here, so this is now BC. We just said this was 2, and this 4 minus the, this is BC here, so this would be 6. So we know this distance here is 2. So it's just a 45, 45, 90 triangle. So it's going to give us, what is it? Root 2, right? Yeah. So that's what the angle is for BC. Or we can just divide by 2 and we have root 2. So now that we have that, we can start doing some of the forces here. Obviously, we already looked at what the angle was there. So let's move on to another page. So are some of the forces in X? Well, remember AB here is acting down and to the left, so in the X direction it's negative, whereas BD and BC are both going to be in the positive direction. Okay. So let's see. Back for a second here. This was at an angle 12 and 6 root 5. So we can use that. So we have a negative 12 over 6 root 5 times, that was AB, and then plus 12 over 6 root 5 times BD, which makes sense since they're both in line, they would both be multiplied by the same coefficient there. And then also in the X direction, we're going to have part of BC, so that would be plus 1 over root 2 BC. And all of these added together would just be equal to 0. Some of the forces in the Y is going to be pretty similar. Okay, so we have the -2 forces acting down on the point on the joint there. We have now a minus 6 over 6 root 5 AB plus 6 over 6 root 5 BD minus 1 over root 2 BC is equal to 0. And so now, since we know AB, this actually just becomes a problem where we have 2 equations and 2 unknowns. So we can actually do this using a matrix method here, or you could just solve for one of the values in terms of the other. But I think Professor Castle wants me to go over some more examples having to do with matrices. So let's try to turn this into a matrix problem. So we draw this as a matrix. Let's see. So we're going to have our columns for BD and BC. And then this is some of the forces in the X, some of the forces in the Y. We're going to multiply by these. So BD, BC. And then we have, it's equal to our solution matrix here. So let's see. So if we add 12, if we add this term over to the other side here, that's going to be part of our solution matrix. So let's see. We have our 12 over 6 root 5 from here. And we have 1 over root 2, which just draw this matrix a little bigger. Okay, so that's are some of the forces in the X. That's going to be equal to 12 over 6 root 5 AB. So let's check back what that value was.
So you don't put the, is it negative 12 over 6 root 5?
Because we're adding this to the other side, it's going to be plus.
Okay. So then the BCs, don't add the BC to the other side?
No, like I'm just, since we know what AB is, we're just adding that to the other side. So let me just, hold on, I'll show this in a second. So we have our AB here is negative 7.8262. So we're multiplying that by negative 12 over 6 root 5. And that turns out to just be 7. So I'll write the equation over again here. So 7 plus our, 12 over 6 root 5 BD plus 1 over root 2 BC is equal to 0. And obviously if we move this to the other side, now our equation becomes 12 over 6 root 5 BD plus 1 over root 2 BC is equal to negative 7. So I only moved the 7 to the other side because this is part of our solution. We know what AB is, and we're not taking that into account for our matrix here. So basically we're just taking these equations that we got for fx and fy and turning them into a matrix. So when you're doing a matrix multiplication, it's just this value times this value plus this value times that value. And then that's equal to this. So this is just simply putting this equation in terms of a matrix. So you don't need to move everything over to one side. So now when we do our sum of the forces in the y, we have a minus 2 here, minus 6 over 6 root 5. So let's check what that is. So it turns out to be, this is plus 3.5 minus 2. So a minus 1.5 on the other side. And then we can just plug in our values here. So this was 6 over 6 root 5, and then negative 1 over root 2. Now, if you're using MATLAB, you can just plug in this coefficient matrix, plug in the solution matrix, and do a left divide command. So you would say like this is A. So you'd say A is equal to, and then enter this as a matrix. This is B, and then you would have A. Let me think. Just trying to think about. Okay, so yeah, it would be A backslash B. So that's what it would look like if you were to do it on MATLAB. I'm just going to do it on my calculator. But yeah, if you normally want to do it, that's how you do it on MATLAB, or you could do it in Mathematica as well.
What is a linsolve? Did you use linsolve on MATLAB?
Linsolve.
Yeah, that's what I used before.
Yeah, that's what I used to do.
Yeah.
Let me just check what that is first. Yeah, it looks like you could probably do that as well. Yeah, I guess it doesn't matter which one you do. The whole thing about using left divide is the program LinSolve probably only solves it for certain cases. This will solve it regardless of what case it is. This is a more general function for solving matrices, whereas LinSolve is more specific to only solving linear ones. You can do it either way. It should work because you're only working with linear ones, but just in general, it's probably better to do it like this.
I got a question. So that left divide, will it work if your matrix is not square?
Let me think. Matrix isn't square.
It's not a square matrix?
No, I don't think it would work for that because, let me think. Like, I'm taking a class on this stuff right now, dealing with a lot of specific things, and there are a lot of problems where you're solving for a non-square matrix, but I don't think left divide would do that. It would give you an error because to solve for part of this, you need to take a determinant of the matrix, and you can't take a determinant of a non-square matrix, I guess.
How would you solve like a non-square matrix then?
Well, okay, so
We're
we're actually doing that in, you'll do that in computational mechanics. It turns out it comes out to a bunch of summation equations. Yeah, it's kind of complicated, but
okay.
you do that for, like, let's say you have a bunch of points and you want to try to make that into a line. You do a least squared regression, and that turns out to be a matrix of summations of like their distances, and so you can solve it by doing that. But because there's more points than there are unknowns, you end up with a matrix that isn't square essentially.
Okay.
So you'll have fun looking at that in the coming semesters.
All right.
Let's see. So I just have a solver on my calculator to do this for me. So I just have to enter the values and it will solve. So basically, this just gives me VE is negative 6.3355 over the dimensions here, kilonewtons. And then we got DC equal to negative 1.8856 kilonewtons. So there's two more of our values here. Now this is a really long problem, so I think I'm just going to move on from this because basically you're just doing the same thing at each point. I don't think he's going to give a problem like that to you because he doesn't want to, it would take too long, and he doesn't want you to have to do a bunch of these matrix problems. Unless, I don't remember him saying there would be anything dealing with matrices on the exam, did he?
No, he said just it's good to know for our next course.
Right. So one other thing that he's been talking about for your next course is a lot of you will probably be taking fluid mechanics within the next 2 semesters, so it made sense that he was going over some fluid problems. So I figured I'll just briefly talk about some of the stuff he's talking about. He actually did make a bit of a mistake, I think, in his class. So let's say you have a problem where so this is your water line, and you have, Uh, oops. Okay. Let's roll stuff around. Okay. So let's say you had a problem like this. So we actually did do a lot of problems like this in fluid mechanics, except with one big difference. In his version here, he was showing that there was water on both sides, yet he was saying that it was just one force acting here, but in reality, if there's water on both sides, we would have the exact same thing on each side. They would both just be pushing in on it equally. So when you're doing this in fluid mechanics, a lot of the times, instead of just being submerged here, it's going to be held in place. So let's say this is a wall here, and there's no water on this side.
It's kind of like a dam.
Yeah, exactly. So we have a pin here, we have this, and then we're going to have some sort of, latch here that's holding this in place, and then you have a wall around the rest of it. And so there's no water on this side. So when you're doing the analysis of this, the forces are all right here, and you're trying to figure out what force this latch needs to provide to keep this door from swinging open, essentially. So I guess I could go into a problem like this. So let's see. So the main thing to remember about this is it's basically all about doing a linear curve here. So obviously that's linearly increasing with the depth. So we'll just call this W like in class. Let's see. So we're going to say Y is measured from here, and H is also measured from here. So let's see. We'll just give some random dimensions here. So let's say this is 10 meters. This is 5 meters long. Okay. So this W is related to Y. It is determined by the distance measured from the top. Okay. And so like you said, you're going to simplify this down to a single force acting at a distance. I don't know, in fluid mechanics, a lot of times you'll call this something like Y resultant. I think that's what you said in class as well. So that's like the resultant force due to all of these forces acting here. Or you could call it H resultant because H is measuring the same thing. So let's start trying to talk about how you would figure out W of Y. Okay, and so I'm just measuring this from here. So obviously you need a density here, this is rho. So we know it's linear, so we just say Y is mx plus b. So let's see. Or actually would be W is my plus b since it's a factor of y. Or it's determined by how far down you go. So first thing we want to do is we know that the force here is rho GH. So let's see. So we can write that, write this as force 1 is equal to rho G, and then its H is 10 here. So it's going to be 10. And then down here, we have rho G times 15. So if we plug both of these into our formula here, that will give us M and B. So let's see, W of 10 is equal to M times 10 plus B, and that's equal to rho G times 10. And then we do the same thing here. W of 15 is equal to M times 15 plus B is equal to rho G times 15. And so now we have a system of two equations with two unknowns. Obviously, you would know what rho and G are. I guess I'll just, for simplicity, just say rho is equal to 1 and G is equal to 10. And so we can plug this in to solve for our M and B. So let's see.
What does the G represent?
Gravity. So yeah, it'd normally be like 9.81, but I'm just going to do an estimate here.
Okay.
Just to make it simpler. So we have 10m plus 1b is equal to 1 times 10 times 10. So here, I'll write 10. Okay, so these are the m's, these are the b's. Okay, so rho is just 1 times 10 times 10. We have 100, and then this is going to be 150. So we have 10 plus 1b, 15 plus 1b is equal to 150. I guess I didn't need to do a matrix here. You could have just subtracted the two equations, and that would have canceled out. So, but I may as well go over matrices as well. Let's see. So this just tells us let's see. So this just tells us M is equal to 10 and B is 0. Okay. So let's see. Oh, I see what I did wrong. So let's see. That would be, if you're only concerned with looking at it from this perspective. So let me just rewrite this then, as H is being measured from here. So this is still true, but then we want H is Y minus 10. So we just solved, we said W of Y is equal to 10Y. But if we plug in, now we want it W of H, we end up with 10 times H plus, or no, sorry, we still want it in terms of Y. But we plug in our value for H here, and that's going to give us 10 times H plus 10. And that makes more sense. Now we have a B because obviously it doesn't start at 0. It starts at our distance H here. So that'll give us our WY here. And then to get our value for that, we need to do some integrations. So let's see. So we do the integral of w from, let's see. I guess I'll do this in terms of h here. So I might be writing this somewhat differently from how he did it in class, but basically, in terms of h, we're starting at 0 and going 5 meters down. So we write the integral from 0 to 5 of w dh. So this is equal to the integral of 0, or from 0 to 5 of 10h plus 100 dh. This is 5h squared plus 100h, and it's going from 0 to 5. So it's equal to 5 times, let's see. Oh, we just need to plug in, since at 0 it's going to be 0, we just plug in the 5 to get our value there. So let's see. Be 5 times 5 squared plus 100 times 5. Yeah, 625. Okay. 625. So that's our first. That's the resultant of the entire, or that's the magnitude of the resultant force here. Now we need this distance YR. So I'll move on to the next page for that. So we want now that same thing times the distance. So let's see. We still want it going from 0 to 5. This time we want it h times what we just solved for. So this will be h times our 10 times h plus 10. dh. And I'm not going to write out this whole thing. I can just do this integral here. Let's see. Okay, so this just gives us 1666. 6 repeating. So it's, or it's 5,000 over 3. And then we're just going to divide that by our resultant force. So that was the 620, or sorry, 670. No, that's 625, sorry. Divide that by 625. That'll give us give us 2.6 repeating. So what that measurement is it's just a measurement from the top of the gate to where the resultant force is acting. I think in class he probably did it the other way around, where he just did it from the water level to where it is. It doesn't matter. It's still going to give you the same result. It's just you would add 10 to it there. So if you wanted to do it in terms of y, I can do that as well. So our w of y was just 10y there. So let's see. So instead of doing it from 0 to 5, we would do it from 10 to 15. 10 to 15 of 10y dy is, what is that? It's just 5y squared which gives us our same 625. And then 10 to 15 of, now we're multiplying 10y by y. So that'll give us 10 over 3y cubed from 10 to 15. So let's see. Just make sure that that gives us the same value. Did I do something wrong here? I'm not getting the same value. Well, let's see, did I? Oh, right. No, you shouldn't get the same value for this because we're measuring it from the water level. So now this gives us 7916.6 repeating. And if we divide that by our 625, we end up with 12.6 repeating. But instead of measuring from the top of the gate, that's measuring from the sea level here. So that makes sense because, let's see, what did we have? We had 2.6 repeating. So obviously the gate is 10 meters below the water. It makes sense that it's 10 higher. Okay. So are there any questions about this? I think we're just about out of time here. Any questions about anything else?
There was a problem he gave, that Professor Castle gave in my homework where it's like you have to solve for a particular member JD. Now I was trying to go about that with method of sections, but I wasn't too successful at it. So
You have it up?
yeah, I can pull it up right now. Give me 2 seconds.
He's gonna do space trusses as well, right?
Right. Yeah, so for space trusses, it's basically the same as any other truss. It's just the biggest problem you might have on a test is they take a long time to do, and you might have a hard time visualizing forces are acting. So you just got to be very complete about drawing everything out very well and making sure. Let's see.
I'm going to solve for this member JD.
Okay.
So how I went about it was okay. So when you use the method of section, you can cut through no more than three members. And so I chose these 3 right here. But I didn't turn out so successful with it though.
Does he give a problem number? Oh no.
Yeah.
Because I have a feeling there's something like this. Let me just check.
Okay.
Because I think it might be a little bit more complicated than just doing a
Single cut.
yeah. You might have to solve for more numbers than that. Let me just check around here.
Okay, thank you.
Sure. Yeah, the solutions manual opened on my
Oh man, that's what's up. See, I thought, okay, I cut through 3 members. That means you're going to have like 3 forces.
Yeah.
You have to solve for, but you're looking for 1.
Oh, wait, let me see one.
But you can eliminate 1 force if you take a moment about this or a moment about there. And now I just reduce it down to 2 forces, 2 equations. It's still not like, what the fuck?
Actually, let me think about this for a second. Are you able to just take? Yeah, I think it's more complicated than just doing one
cut,
section there.
1 cut, okay.
But there is something interesting about that problem, which is that it's all pretty much symmetric.
Right, it's very symmetric.
So, like when you're doing it in the forces in the X, like this member would cancel with that
That one,
member,
right, exactly.
and that member would cancel,
Cancel with that one. And this
So-
one equals that, well, the y component here equals the y component there.
Right.
Yeah.
So there might be, you might be onto something. There might be a simpler version. I'd have to look at it for a little bit longer.
Okay.
But I'm not entirely certain about that. But yeah, there probably is some way to just do a section there, since you don't want to have to try to solve for
Every joint, that's going to take like, that would take hours.
So yeah, I'm pretty sure there would be some way to do
Yeah,
that.
'cause that's the only one that kind of stumped me in the problems. I'm like, damn it.
Yeah, yeah. That's the annoying thing about some of these problems is like there's a lot of times not a very easy looking solution, and if
Yeah.
you can't figure that out, then you're stuck having to solve for like 20 members.
20 members,
And
right?
like it's like I don't want to
do that.
solve
Right?
this.
That's
this
like,
whole
that's
thing.
overkill.
Yeah,
You know, I mean, I wish you gave it like the solutions.
yeah.
You know,
That would be nice.
that would be so nice.
Yeah, it was like that. I took dynamics last semester, and it was the problems were ridiculously hard. And luckily, he gave solutions, so I could figure it out once it was time for a test. But like when I was trying to do the problems on my own,
yeah.
I had no idea what
Exactly,
I was doing.
man. I'm like, yeah, for real. I don't think I'm gonna ask the president. Just give the solutions. I mean, if you get the answer, you can give the solutions.
Ask the TA.
That's
The TA
it.
should be able to give
I've
you a
never
solution.
met the TA class.
Yeah, I don't know who it is either.
Yeah, I'm like, who the hell is this guy?
Yeah. Okay. Let me
He hasn't even made an appearance.
Yeah.